Hello everyone. Welcome to today's session. In today's session, we'll be discussing the aerodynamic problems from GATE 2016. So let's get started. So the distribution looks something like this. So there are around 5 1 mark questions and two marks for 4 2 mark questions. That's around 13 marks from the aerodynamics section, so which is it's actually quite substantial. So let's go ahead. So the first question: with increase in airfoil thickness, the critical Mach number for an airfoil is likely to. So critical Mach number is nothing but, let's say, if you have an airfoil and the critical Mach, we know that, uh, let's say, if there's some free stream velocity, right? Or let's say free stream Mach number. Now we know that your flow will accelerate on top of your airfoil. And so what can happen is that if your free stream Mach number is quite large enough, but subsonic, let's say it's some subsonic Mach number less than 1. So what is that value of the subsonic Mach number, which when passing on top of your airfoil starts creating, sonic velocities on top of your airfoil because of the acceleration. So that is basically your M critical. So what is that first initial value of Mach number, subsonic value, which will start creating sonic velocities because of flow acceleration on top of the airfoil. That is basically what they mean by critical Mach number. And what they're asking is, let's say if I have a thin airfoil and then maybe like a thicker airfoil, right? What will happen? And maybe you can consider they have the same shape. What will happen to this critical Mach number? Does it decrease, increase, uh, remain the same, um, or it cannot be defined? So let's say, imagine this in this case, the critical Mach number is 0.8 as an example. Now imagine I use a thicker airfoil of the same shape, let's say. Now would this remain as 0.8 or would it reduce, increase is basically the question. So in this case, the critical Mach number will actually reduce. So your critical Mach number from 0.8 might reduce to, let's say, 0.6 or 0.7 or whatever that number is. And the reason being that once you have a thicker airfoil, your thicker airfoil is, and you know that it is basically the um, curvature and then the turning of your uh, flow by your airfoil that is actually accelerating your flow. So in thicker airfoil, that is actually going to turn your flow more. That is actually going to cause more, drastic changes in the direction and higher acceleration on your flow, and hence the acceleration of your flow. Hence the increase in speed of your flow on top of your airfoil is going to be much higher. So though you start at a lower Mach number, the acceleration would be substantially higher, and hence you can basically start getting sonic velocities even at low values of pre-stream Mach numbers. So in the right option here is basically option A, that your critical Mach number will actually decrease. All right. Any questions on this? Go ahead. Due to a body in potential flow, the velocity at a point A in the flow field is 20 meters per second, while the free stream velocity is 10 meters per second. The value of pressure coefficient at this point. What they're saying is that there is a potential flow field. All right, there is some flow field which is potential. All right, and they're telling you there's a point A in that flow field. And the velocity at this point, VA, is 20 meters per second. And the free stream velocity is 10 meters per second, right? So they're asking you what is the value of pressure coefficient. And we know that pressure coefficient, uh, which is actually defined as P minus P infinity divided by Q infinity, which is your dynamic pressure, can be written in the form 1 minus V square by V infinity square, if it is a potential flow field, right? So in our case, it's a potential flow field, so I can write my Cp in the form of velocity like this. So Cp is nothing but velocity at the point of interest, 1 minus velocity at the point of interest square by the free stream velocity square. So here Cp is 1 minus, your velocity is 20, square it up, your V infinity is 10, so we square that up as well. So your Cp will basically be 1 minus 4, your Cp value would be a very simple problem. Okay, guys, any questions? There's a confusion. Will we put negative sign? Um, how will you put negative sign in the sense? You mean as the answer? I think you typically in the GATE exam they'll ask you to give a range, right? Um, so let's say they would ask you to give a range between, let's say in this case you could give it as minus 2.9 till let's say minus 3.1. And in many questions they'll only ask you the magnitude, but in this question they're actually asking you what is the value of the pressure coefficient. So you would actually need to give like a range, like you need to give it with the sign. So you can give it in a range like minus 2.9 to minus 3.1 or something like that. Right. So the following airfoil will have a location of the maximum camber at half chord length um, from the leading edge. So what they're asking is, there are a bunch of airfoils given over here: NACA 5212, 1225, 2215, 2512. They're asking you which airfoil will have the location of maximum camber at half chord length from the leading edge. So they want an airfoil whose location of maximum camber is at a distance of half the chord length, e by 2, right? Or in other words, 0.5 C. That should be the location of the uh, maximum camber. So we know that it's a NACA 4-digit series. In NACA 4-digit series, the first digit would basically tell you what is the maximum camber, and second digit would tell you what is the location of the maximum camber. So second digit, uh, let me just write it down. Second digit, uh, you divide it by 10 and multiply it by the chord, will basically give you the location of maximum camber, right? So in all the given options over here, you can see that in this case it will be 2 by 10 into C. So that would be the location of maximum camber, but we are basically looking for, and that is 0.2 C. But we want an Airfoil with 0.5 C as the location of maximum camber. If you scan through all the second digits over here, in option D, you can find that it's NACA 2512, second digit is 5. So you get 5 by 10. C as the location of maximum camber, which is something like 0.5 C. Right? So option D is the right one over here. So a thorough understanding of the NACA nomenclature of at least 4 series and 5 series is required for the GATE exam. They can ask questions from it. Right? Any questions here? Then the next question, what they're asking you is, for a laminar incompressible flow past a flat plate at zero angle of attack, the variation of skin friction drag with Reynolds number based on chord length C can be expressed as. So you have an incompressible flow past a flat plate. So there's a flat plate, then incompressible flow. They're asking the variation of skin friction drag. What is the skin friction drag CF? And how does it how is it related to the Reynolds number based upon the chord of your airfoil? Based upon the chord length, or in this case, let's say length of the flat plate. All right, and the flow is at a zero angle of attack. So we know from Bloch's solution to the boundary layer that your coefficient of skin friction is nothing but point. This can be approximately calculated as 0.664 by root of Reynolds number times, whatever the length that you want to calculate it to, whatever point on the flat plate, location on the flat plate, maybe here. Basically, X is nothing from the distance from the leading edge, right? So from this, we know that the coefficient of skin friction is inversely related to the square root of Reynolds number from the Bloch's solution. So that basically leads us to option C as the right answer, that the coefficient of skin friction based upon the chord length can be expressed as 1 by root of Reynolds number based upon the chord length. All right. Yes. Go ahead. Question A. Air with Prandtl number 0.7 flows over a flat plate at high Reynolds number. Which of the following statement is true? So thermal boundary layer is thicker than velocity boundary layer. Thermal boundary layer is thinner than velocity boundary layer. Thermal boundary layer is as thick as the velocity boundary layer. There's no relationship between thickness and the thickness of thermal and velocity boundary layer. So, one thing which we need to understand about the concept of Prandtl number. So let's say if I write Prandtl number PR from the equation wise, it's nothing but mu times Cp by K. All right. And Prandtl number is also defined as the ratio of thickness of velocity boundary layer to the thickness of thermal boundary layer. All right. So let's say you have a scenario where you have a flat plate which might be heated. All right, your free stream is coming in at, let's say, 10 meters per second, and it is coming at a velocity, let's say 300 Kelvin, right? and your flat plate is, let's say, 310 Kelvin, right? Now you'll definitely have a velocity boundary layer, where velocity is zero at the plate and then increases to free stream. And on top of that, you'll have something called as the thermal boundary layer as well. So let me just diagrammatically represent. So that is nothing but how the temperature is trying to diffuse to your free stream. So your temperature will be 310 Kelvin at the flat plate location and will slowly go to 300 Kelvin as at the free stream. So this is what we call as a thermal boundary layer. That is, the thickness or the vertical distance that is taking for the temperature to go from 310 Kelvin at the uh, flat plate to 300 Kelvin of the free stream. So, so the temperature is also kind of diffusing into your flow, just like your momentum, because of which you get a velocity boundary layer, right? So Prandtl number is basically the okay, it's kind of a representation where you have the thickness of the velocity boundary layer to the thickness of thermal boundary layer. And now they're saying air has a Prandtl number of, let's say, 0.7. So if my Prandtl number is less than 1, it means that uh, my velocity, the thermal boundary layer, is actually thicker than my velocity boundary layer, right? Because my denominator is going to be definitely larger. If air has a Prandtl number 0.7, which is less than 1, it means that the thermal boundary layer is thicker than the velocity boundary layer. So option A is the right one over here. All right. Any questions here, guys? Questions, confusions? Now on question 29, what they're asking you is the maximum value of coefficient of lift for a 2D circular cylinder, provided at least one stagnation point lies on the cylindrical surface, predicted by potential flow theory to be. So what they're telling you, imagine you have a circular cylinder, which is 2D. There is a flow over it. And then there are basically um, uh, your stagnation points are lying on the surface of the cylinder, let's say, in this way. Actually, provided at least one stagnation point lies on the surface of the cylinder. So we know that for a potential flow over a cylinder, we have multiple solutions where there are two stagnation points, or if my circulation is large enough, I can get one stagnation point, or cases where there is one stagnation point inside and one stagnation point outside, which is not like a physically possible scenario, right? So they're telling you, asking you, what is the maximum value of CL over this 2D cylinder, such that at least one stagnation point lies on the surface, and based upon potential flow theory. So CL can only be produced by a lifting flow over a cylinder, right? Basically the one with circulation imposed on it. The CL is given according to your potential flow theory. The CL over a 2D cylinder is given by gamma by R times V infinity. Now, we need to figure out what this gamma will be. All right. So we know that the location of the stagnation point is given by sine inverse of minus gamma by 4 pi infinity r, 4 pi infinity times the radius of the cylinder. All right. Now they're telling you, so only if gamma is greater than 4 pi v infinity r, my solution will be this not physically possible kind of solution. But if my gamma is less than or equal to, all right, 4 pi v infinity r, I can get actually physically possible solution out of it. So if my gamma is less than 4 pi v infinity r, I get 2 stagnation points. If my gamma equals 4 pi v infinity r, I get 1 stagnation point. And my CL is directly proportional to my gamma. So which means that higher my gamma, higher is my CL. So for a physically possible solution that contains 1 stagnation point on the surface of my cylinder, my gamma, maximum value that my gamma can take is 4 pi v infinity r, right? That's the maximum value of gamma that I can have and have physically possible solution and then have stagnation points on the surface of my cylinder. So I substitute this maximum value of gamma max, all right? So hence my CL max would be nothing but 4 pi v infinity r divided by r into v infinity. You can cancel out the v infinity, you can cancel out the r. The maximum value of CL will turn out to be 4 pi, right? Which is nothing but option D. Right? Yeah, it might look like a very tricky problem, but once you write down all your equations, you can easily break it down. All right. Yeah. Any questions on this case? These are confusions. So let's look at this problem. Nozzle AB, as shown in the figure below, the leading to a test section of a low-speed subsonic wind tunnel has a contraction ratio of 10:1. So it's a nozzle which has a contraction ratio of 10:1. The pressure difference across the nozzle is maintained at 1,000 Newton per meter square, and the density of air is 1.23. Assuming one-dimensional steady inviscid flow, the velocity in the test section as measured at point B is. So they're basically asking you what is the velocity at this point B. All right. To solve this, we need to use a combination of Bernoulli's equation and it's a low-speed subsonic wind tunnel. So we can use our incompressible equations over here. So again, you need to use the Bernoulli's equation as mass continuity equations between point A and point B. So writing down my mass continuity equations, so I have rho A VA into the area at location A equals rho B PB into area at location B, right? And it's going to be an incompressible scenario because it's a low speed scenario. So rho A and rho B will be equal. A equals rho B, which is nothing but 1.23. So hence I have VA and equals VB AB, right? VA area A equals VB into area B. And let me apply the Bernoulli's equation between point A and point B. So that would be VA plus density. I'm going to just take it as a rho. Rho into VA square by 2 equals VB plus rho into VB square. All right. Now we want velocity at location B. So I'm going to write VA in terms of VB. So VA is nothing but VB into AB by AA. Sorry. All right. So I'll just replace my VA from here. That is PA plus rho into VB square into AB square divided by AA square by 2 equals PB plus rho into EB square by 2, right? So I'm going to take all my VB to one side, and then I'm going to take all my PA and PB to the other side, right? So I take PA minus PB equals rho by 2 into VB square into 1 minus AB square by AA square, right? And we know the contraction ratio is 10. So AA by AB is nothing but 10 is to 1. So AB by AA is nothing but 1 by 10. And you know PA, so the pressure difference across the nozzle is 1000 Newton per meter square. So you know what is PA minus PB. You know what is rho. You know what is AB by AA. So only thing unknown is VP. So if I were to just put in the numbers, 1000 equals 1.23 by 2 into 1 minus 1 by 10 square, which is 100 to VB square, right? So your VB will be equal to square root of 1000 into 2 by 1.23 into 100 divided by 99. So just this cross multiplication, you would need to do, right? So your VB will turn out to be a value around 40.5 meters per second. So very simple and straightforward, and that's basically what they want: velocity at section, velocity at the point B. Right? Any questions here, anyone? Go ahead. The next question: the rate of change of moment coefficient with respect to angle of attack at half chord point of a thin airfoil as per approximations from thin airfoil theory is. So we're asking you, consider a thin airfoil and go to the half chord point of it and tell me what is the rate of change of moment coefficient with respect to angle of attack. All right. So this is basically the question. So you know that the moment coefficient for let's say, and then they've basically told you that they are basically looking for the moment coefficient at the the half chord point. And let's say if you take from thin airfoil theory, your moment coefficient Cm, let's say at the leading edge for any shape of shaped airfoil, let's say it might be symmetrical or cambered, will have an expression like this: minus Cl by 4 plus A1, A2 minus A1, which has some coefficients that depends upon the shape of the airfoil. All right. So this is what we know from thin airfoil theory. So this is the moment at the leading edge. All right. Now we need to find the moment at the moment coefficient at the quarter chord point. The moment at the quarter chord point would be nothing but so if I have my lift force also acting up here, so it is nothing but moment at the leading edge, and you need to transfer this force as well, which is nothing but lift into the distance, which is c by 2. And if I convert them to non-dimensional form, so this would be nothing but coefficient of moment at the half chord point. It's equal to coefficient of moment at the leading edge plus PL by 2, right? And coefficient of moment at the leading edge is nothing but minus CL by 4 plus A2 minus A1. A2 and A1 are some shape based parameters plus CL by 2, right? And we know that your for a thin let's say for any airfoil, let's say symmetric or for a cambered airfoil, your CL is nothing but 2 pi into alpha minus alpha L equals 0, right? And for alpha L equals 0 will be 0 in case if it's a symmetric airfoil, or it will have some negative value if it is not. All right. So let me just replace that. So minus CL into 2 pi. So if my CL is 2 pi into alpha minus alpha L equals 0. So I can basically, so before I do this conversion, what I can do is I can, subtract CL by 2 and then, CL by 2 from here. So this would be nothing but minus CL by 4 plus CL by 2. So that will be again CL by 4. All right. So that I do. And then I have plus A2 minus A1. This is
Sir, please little louder, sir.
Louder? Okay. Yeah. So what I'm basically doing is just subtracting out CL by 2 minus CL by 4. That gives me CL by 4 plus A2 minus A1. All right. Now CL, I'll be replacing it with 2 pi alpha minus alpha L equals 0. So my coefficient of moment at the half chord point would be nothing but 2 pi into alpha minus alpha L equals 0 divided by 4 plus A2 minus A1. All right. And they're basically asking you what is the rate of change of this with respect to angle of attack. All right. So I want dCmc by 2 by d alpha. All right. So if I I differentiate this first term with respect to angle of attack, this is independent of angle of attack, and this is the only this is a linear function of angle of attack. I'm left with the 2 pi by 4. And this function, if I differentiate with respect to angle of attack, they are only depend upon the shape of your airfoil. It has no relation to your angle of attack. Once I differentiate, this becomes 0. So I can cancel these both. So finally, my answer is pi by 2 per radians. All right. So the right option here is option B. Right. Any questions, confusions here, guys? All right. Let's go to the next problem. An untwisted wing of elliptical planform and aspect ratio 6 consists of thin symmetric airfoil sections. The coefficient of lift at 10 degrees angle of attack, assuming invested in compressible flow, is. So what they're saying is you have a wing of elliptical planform. All right, your wing is elliptical in shape, and the aspect ratio is 6. Right, and it is created out of thin symmetric airfoil sections. So every airfoil section is a thin and symmetric airfoil. Right. Now what they're asking, what is the coefficient of lift at alpha equals 10 degrees? All right. Now we know that if since the airfoil is thin and symmetric, the lift curve slope of the airfoil would be A naught would be around 2 pi per radians. Right. It would be 2 pi per radians. And once we create a wing out of this airfoil, you know that your uh, uh, lift curve slope of my wing will be related to lift curve slope of my airfoil as A naught divided by 1 plus A naught divided by pi into aspect ratio times the efficiency factor. In this case, we have efficiency factor to be 1 because my wing is elliptical in shape, which has the highest efficiency. Right? So I'm going to replace my A naught with 2 pi, right? And then I have my do that in the denominator as well, divided by pi into aspect ratio is 6, and efficiency is 1, right? Cancel out these, I cancel out this 2 and 6. So my lift curve slope then becomes 2 by 3, 2 pi into 3 divided by 4. If I do these fraction multiplication over here, I can cancel out these two. So this becomes 3 by 2 pi per radians. So you can see once we once we are trying to calculate for the entire wing, from 2 pi it reduced by 0.5 to 3 point over to 1.5 pi. That's the reduction because of the downwash effects. Now they want us the lift coefficient, which is equal to A into alpha, because it's a symmetric airfoil, so it does not have zero lift angle of attack. So A is 3 by 2 pi, alpha is 10, which you need to convert to radians by multiplying it with pi by 180. Right? By 180. So I cancel this out, and this guy. So I'm left with pi square by 12. And non-dimensional because it's a CL value. Right? The right option here is option B, pi square by 12. Right? Questions on this, anyone? So that is all the questions that we had. So this particular year, we had quite some number of questions from the aerodynamic portions. But as you can see, they are not very complicated. You can, if you know the right formulas, if you know the right concepts, they're very, very simple, and you can solve them maybe in less than a minute in most cases, even the 2 mark problems. All right. So yeah, that's all for today. Yeah, thanks for uh, joining in. The equation we use for pure stream function and non-pure stream function. What do you mean by pure stream function? I am not very familiar with the term pure stream function.